Okay, well, welcome to the fine world of clustering. I don't know what useful hour number we're up to at this point, but I figured that clustering was something that was better to talk about earlier rather than later, because a lot of people use clustering, but a lot of folks have no notion at all how it works. So I thought that today we would talk about two different kinds of clustering, sort of a top-down approach that we call K-means clustering, and a bottom-up method called agglomerative clustering. Both of these have user interfaces built into R, and we'll also look at some ways to evaluate the results that come back from clustering. I think folks may remember from a few weeks back that we talked about the use of the Iris data set. It's a very common one, and it has some nice ambiguities in two of the species that have very related petal length and widths. So I think that that'll be a pretty good set for us to work with as a starting point for today. Okay, so I've started R here. I'm not really using any special libraries per se, but I will be kicking off ggplot2. So let me do a little bit of setup for that. I have I've taken today's presentation from a couple of blog entries. I wanted to note that one of the things that you're going to want to do is a little bit of data cleaning beforehand. So having the ability to strip out things like not applicable values, those NAs will really cause you some grief if you try to cluster on that. So make sure that those are scrubbed out of your data set. The other is that scaling matters, because in a lot of what we're talking about today has to do with our ability to compute distances. So if you have one variable that scales up to 1,000,000 and another variable that scales only between 0 and 1, one of those is going to drive those distances rather hard. So being able to rescale in a way that these different axes are comparable will be helpful. Okay, so I'm going to open up two libraries, the one called datasets and the one called ggplot2. So that's just a matter of calling library datasets and library ggplot2. No problem there. And we're going to start by looking at the dataset called Iris. Okay, so I've kicked off. Okay, so Iris has several fields for us to work with. I have my pointer right over here. There we go. Okay. So we have sepals and petals, and we have a species indicator. So these are measurements of sepal lengths and sepal widths. These are petal lengths and petal widths, and then we have a species name that's been associated with it. We can do a summary of that, and you'll see that there are, I think, 50 different Variosa, Setosas, and I forget what the other one is off the top of my head, but we've got 3 different species that are all here. I've used ggplot to do a little plot of petal length versus petal width. We have more metrics in this data set we can work with, but we're just going to focus on these two to keep it a 2-dimensional problem for now. So let's do a quick look at the plot that resulted from that. So remember, we're talking strictly about petal length and petal width, and we see Setosa, versicolor, and virginica. These are the 3 different species within Iris, and we see on that the Setosas down here have the smallest petal lengths and the smallest petal widths. We have versicolor showing up somewhere in the middle, and then we have the blue set up here, virginica, that has the longest petal lengths and the longest petal widths. But we also see there's a bit of crosstalk here. I don't know how clear the colors are back there, but you can see that we've got blue here, 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 and here, and here, but we have some green creeping in here as well. So you can see that's going to cause a bit of a problem as the software tries to disentangle that to different clusters. All right, so that's why it's a reasonably good data set for us to test these algorithms in these contexts. Okay, now we're going to start with a K-means clustering algorithm. So K-means is one of the most common methods used for clustering. It is a top-down approach, essentially. First off, K-means is distinctive in that it's going to ask you how many groupings should exist within this data set. If you tell it to find 4 species and you have 3, the software will do its dead level best to give you 4 different species based on the data. So you must have in mind beforehand how many different clusters it should have to run. Okay, the next is that it starts as it is a random iterative algorithm. So it's going to have a series of starts that we have to apply. We're going to tell it in this case to do 20 starts, and each one of those starts will be a random association of the data sets, of the different data points to clusters. So if you specify a random start with 3 clusters, the software will randomly assign labels 1, 2, and 3 to each of the 150 species that we have here, 150 different plants that we have. So those random starts are obviously pretty bad clusters, typically. They're just random. But the software then attempts to iterate through kind of an optimization process. So I mentioned already that we were going to care a lot about distances along the way. And this is a good place as any to talk about the concept of centroid. So having assigned these 150 dots to 3 different clusters with random labels, the software then asks, what is the centroid of each cluster that was randomly assigned? So if you have points all up and down here, probably in this very first starting point, you're going to find that you have centroids for the 3 clusters that are quite close together, because they're just randomly drawn from the set of 150 that we've got. Okay, so having determined what those centroid values are, which is to say a point that is representative of the center of mass for that cluster, so kind of the average x-axis and the average y-axis will be the centroid for that cluster, the software then says, let's now assign each data point to the cluster that has the closest centroid. All right? So having 3 clouds that were randomly assessed, we had some random variation in where those centroids appeared, and now the software is saying, well, if these are closest to one that has a centroid down here, all of these will lump to that class. Likewise, this has a value that's closest to that centroid as well, and so it's going to get lumped into that erroneously. So we've now got 3 centroids with random variation across this space. The points have been reassigned based on where those centroids appeared, and now we regenerate where the centroid is for each of those classes. So you continuously iterate this step of not randomly, the only time you randomly assign data points to classes is that very first iteration. After that, you always assign the data points to the cluster that's got the closest centroid. And then you recompute the centroid and then redo the fits of which points go to which clusters, and you keep going until there's a convergence. As I said, there are 20 iterations that it will go through, 20 different starting points that it will go through, each time choosing randomly. So let's think about what that implies. Let us examine a case where we have a cluster of 90 points that are all sort of typically distributed in, say, a 2-dimensional space. And you have just 10 items that have really extremely high values on either or both of those axes. In a scenario like that, if you tell it to give me a K-means cluster with only 2 classes, the software may struggle to find that second class because those you have only 10 members that are in this outsider group, and it may be that the variation in the larger group ends up driving where those 2 clusters form. So K-means is something that we need to be careful about using, and you probably will need more random starting points if you're trying to deal with data that are not more or less equally distributed. In this case, we have 50 flowers that are each being put into each species, so we don't have this problem of asymmetric distribution. So to restate the K-means algorithm, we're going to start with a random association of class labels. We're going to compute the locations of centroids for each cluster, and then we're going to assign the different members to one of these classes based on which one had the closest centroid. And then we repeat those last 2 steps until we get a convergence. Good so far? All right, so you can think of this as kind of an empirical way to handle the splitting of the data set from the top down into K different sets with K-means. All right, so let's see how this looks in code. Happily, it's actually not extremely bad code, so this is good. All right, so we're going to start by setting a random seed. because this is a random process, the seed with which you're starting the pseudo-random generator matters. We would like this result to be as repeatable as possible, and in this case I'm specifying I'm going to start with a seed of 20. Does that number 20 represent anything in particular? No, I could start with my lucky number, I could start with pi, I could start with whatever I want. But this is just a way to specify where the starting point for the random number generator will be. Not important, but something that you frequently see in code. All right, now we're going to start with, we're going to do 20 different starting points for our cluster. So in R, we are going to we're going to store the result of this function in iris cluster. We're going to run the KMeans function. It's not in ggplot or anything. This is just base in R. We're going to look at iris using columns 3 and 4, so just petal length and petal width. Let me see. We're going to compel it to produce 3 clusters out of the data, and we're specifying 20 different starting points. Okay? So that's all we had to do in order to tell it to create this cluster. Okay. Now, it provided a fairly rich object in response. So I would like to show you what that looks like. Okay. Let me see. Well, I'm not going to show all of the stuff, but you can see that one of the things it came back with was an average petal length and an average petal width for each of those 3 groups. You remember that we had one group that had by far the smallest lengths and widths for petals, and so we can see that that one is being represented by cluster 1. We have a set that has a relatively low petal width, well, this is actually kind of the medium group, and then we have the high group. That's pretty clearly how this is laid out. And you can see that there's a vector here with 150 elements in it, and each of those items, each of those 150 plants, has now been given a rule. Was this part of group 1, was it part of group 2, or was it part of group 3? The way that the data are structured in the R object in the data set has all 50 of the first, and then all 50 of the second, and then all 50 of the third. So you can already see there are some errors here, that some of the associations between the clusters that were built out of KMeans disagree in where these should be. And you also see that there are some figures of merit here. So we have between and outside variance being compared. So that is a useful way to evaluate how quality were these metrics that were built out of it. And we have a whole bunch of different values that have been produced that are available for us to use for characterization. Okay, so let us now look at that in a tabular form. We're going to apply this rule that you see in the clustering vector up here. And now we're going to create a table that crosstabs it essentially, that sets the species field that came from our original data set versus the clusters that were derived from the data. Remember, there were 50 of each of these. So we had 50 setoses. All of those were put in set 1. You remember those red points that were down near the origin? Yeah, they were all grouped successfully as their own separate set. Versicolor was a little more problematic. Versicolor and Virginica were kind of a smear in a way, that we had green dots and blue dots that were commingled. So we see that Versicolor was mostly put in group 2, but 2 of them leaked over into group 3. And Virginica, 46 of them were put in group 3, but there was a little bit of leakage into group 2, that 4 of them were mislabeled there. So having this kind of information is useful in seeing whether the cluster that was derived from the data represent the clusters, the associations that we know, the class labels that we know to be applicable. Okay, so from there, we're going to use the cluster information that came back from K-means clustering and make it into a factor. So we can look at what that is. That's an iris cluster cluster. Okay, so you can just see that instead of being represented as a string of integers, we're representing this as a factor to represent how many distinct values are reported in that cluster string. Use that as a factor for mapping. Okay, and now we're going to do a visualization of the cluster that we derived. Okay, So we're doing a ggplot, and it should show up in another window. Okay. So here we see that before we were using the species to do our labeling of each flower. Now instead we're using the cluster number that came off of it. So before we had a bit of crosstalk between green and blue items, but now you could just throw a barrier across here, and anything below that is the green and anything above that is the blue. So this is another way we've relabeled, instead of doing the species coloration, we're doing the cluster coloration. So we can modify that right back to the original plot by this ggplot command. So I'm going to make this a vertical array for now. All right, I'm just going to replace the image that we had a moment ago with the other one. Okay. So before we were looking at the cluster vector, now we're looking at the species. So we see that this boundary is once again confused. The reality of the data is that there's a little bit of crosstalk in the Virginica and versicolor species definitions. Okay. That is not necessarily the best visualization to work with, because you've got basically this two-cell cartoon that you need to flip back and forth. And in a little bit I'm going to show you a ggplot call that makes it possible to show both the species and the cluster assignment in one visualization. Okay, so let us now switch over to a different kind of clustering. Before, we used the KMeans clustering approach, which required that we knew in advance how many clusters should be there, and then the software attempted to converge on an optimal assignment of our data points to those clusters. With the hclust function, the hierarchical clustering feature that we most frequently see used in R for building our clusters, you don't have to provide in advance this tale of how many clusters there should be. Instead, it's an attempt to build up from the bottom what clusters can be found in our data. So let's imagine that instead of having one cluster or three clusters of these 150 data points, we instead have 150 clusters, right? So each cluster has just one member in it. So in this agglomerative approach for building clusters out of these data, we're going to try to figure out which clusters are closest together that we can infer that they are in fact one cluster. And we're going to keep going through 149 different join processes until all of these 150 clusters of one node have been joined up into a single hierarchy. Okay? And all of this is going to be built around a distance metric. So the distance metric that we most frequently think about is a Euclidean distance. Has everyone heard the term Euclidean distance? Okay. So the Euclidean distance in 2 dimensions really devolves down to the Pythagorean theorem, that we have 2 points in space, in a plane actually. They have some y distance between them, and they have some x distance between them. So if you know the y distance and the x distance between them, you can compute z, the distance from one point to the other in 2 dimensions, by summing together the squares of x and y, and then taking the square root. So x squared plus y squared equals z squared. Okay, so this approach can tell us which of these 150 different units have the closest similarity to each other in this 2-dimensional space. So in the plot, that's just going to be which 2 points are closest together. So having done a complete assessment of all the different pairwise members, we can then say, well, what pair is most subject to being combined? Now, once you've gone through that first iteration, you now have a problem, because you have 148 points remaining, and you have 2 that have already been glommed together in some way. So now we need to be able to find the distance from not each of these points individually, but rather from the centroid of this group to the others. So that that linkage is something that we need to be thinking about as well. It's not just distances between points at that stage, but rather between points and clusters and clusters and clusters. So at each stage, through each of these 149 merges, we're going to combine together the two elements that are closest together in this two-dimensional space. And that's going to build us a hierarchical cluster. Because we'll remember which ones were closest and which ones were furthest away by the order in which those linkages were made. And we'll also know something about the actual distance between those points that we can also use to factor into that. So not just to know that this was the 79th and this was the 78th merge, but that the 79th merge was a much bigger distance than the 78th merge, for example. Okay, so let's look at this code. I'm going to move away our diagram here. Okay, so we're going to apply a bottom-up technique for this purpose. All right, and I'm going to do this in just 2 lines. Okay, so we're going to start by this call to dist. This is the Euclidean distance function. So we're giving it a vector with 2 columns in it. These are petal lengths and petal widths, as I recall. So we're now going to compute distances between each pair in there. Which brings me to the cocktail party problem, and something I talk about quite frequently. If you have 150 different flowers, how many different pairs of flowers do you have? Does anyone know the math? This is the same thing as saying you have n people at a cocktail party. How many different handshakes can there be? So I can't shake my own hand, but I can shake every other person's hand exactly once, right? So there are n-1 handshakes available to any one person at that party. Okay, so next, if I shake your hand and you shake my hand, it's the same handshake, so we can't count that twice. We only count it once. So the math for this becomes n times n-1, all divided by 2. So if you have 150 flowers, you have 75 times 149, effectively, pairs of distances you can compute. So that's doing a fair bit of work behind the scenes. So this function, then, is producing an object that is the return from the distance function, and that gets passed to the hierarchical clustering function. So let's take a quick moment to look at the data structures that came back from that. First off, iris dist is a really, really big table, but it has this kind of unique property that it's a big triangle. Only half of the values are shown up here. And the reason for that is that if number 78 has been compared to 73 once, you don't have to compare 73 to 78 in return. So we only need half of the table filled in to know all of the distances. Okay, so we shan't look at that more, but I will look at the clusters object that came back from our hierarchical cluster. So there are a couple terms that showed up here. I want you to remember that the distance metric we used here was the Euclidean. This is the Pythagorean theorem distance between 2 points. We're going to look at an alternative to that, briefly and very superficially, I'm afraid. The other is this clustering method. So there are a variety of ways that you can evaluate this cloud of dots versus this cloud of dots. And you might think about some of the different ways you could do that. One is that you could compute the centroid for this cluster, and then compute the centroid for this cluster, and ask how far apart are those 2 centroids, just using the Euclidean algorithm. Right? That's pretty straightforward. So we think of that as an average linkage way to evaluate these 2 clusters. So an average distance from one to the other. Actually, the more typical way that we do it is to look at all of the different point-to-point relationships in cloud A and cloud B, and then find the average length across that set. But that's, being pedantic. All right. Well, let's think about another way. We could take the optimist route and say, we care about only the longest distance possible in evaluating the separation of these clusters. So I want to find the greatest distance from any point in A to any point in B. All right? That is what we refer to as complete clustering. We ask what is the longest distance for any point in A versus any point in B. there's also the opposite of that, to look at what is the shortest distance from any point in A to any point in B. But by default, hclust is going to use the complete method, which is to say what is the longest distance from any point in A to any point in B. That will have an effect, and we might take a glance at that as we move ahead. All right, so now we will take a look at the plot that results from this clusters object. Okay. All right, this is called as it appears, dendrogram. So these dendrograms tell us a couple different things. One of these would be the order in which these different plants were merged together. So we can ask which of these forks is closest to the data points down here, and that's the one that happened first. And then you can say that the one up at the top is the last linkage that was drawn between groups. Okay? So here's the first or the last split, the penultimate split, the anti-penultimate split, and so on. So those forks, their positions in the vertical scale, tell us about the order in which these merges were carried out. The next thing that they tell us is that there's some spacing that appears between these different forks, and it's not uniform in spacing. So when we see that this one is closer in scale, that's to say that this was deemed to be a worse split than that, and you can tell to some extent how big how much better or how much worse a split was by this distance in space. So when you're dealing with evolutionary data that have been clustered in this way, one of the things that we try to convey by the distance, the vertical spacing of these forks, is to tell us about the distance in evolutionary space for these sequences as well. Okay, so I'm not going to do a whole lot more on this at the moment, but I want you to think that this is, we're using just basic graphics here, so I don't have a handy labeling of which of these are red and which of these are green and which of these are blue. So let's try to get a better visualization then of whether this hierarchical clustering method gave us good results. Okay, so we're now going to apply this clustering rule and evaluate its effectiveness. All right, so I'm flipping back over to the console. I'm going to throw in 2 lines here. The first is that I've applied the cut tree function. So I had a cluster that was derived from hierarchical clustering. I've now told the software, cut this tree wherever it will produce exactly three separations, 3 different segments. Because we knew there were 3 species here. So in KMeans, we had to tell the clustering, you are going to produce exactly 3 clusters. In hierarchical, you don't have to do that, but you can still apply post hoc the number of clusters that you want to be applied. So our cut tree function produces a cluster cut, and then we can produce a table that shows how cluster cut compares to iris species. So we see that our setosas, once again, these little red dots down close to the origin, they're all kept in their very own cluster very, very happily. But look at this disaster that we've got going on with versicolor and virginica. Virginica looks great, it's all in cluster 2, but versicolor has been split pretty badly between clusters 2 and 3. This reflects that kind of crosstalk that we had to deal with. Okay, so that wasn't ideal. I think I have a visualization step. Oh, no. For this next stage, we're actually going to step away from the complete linkage approach, which is asking what is the longest distance between any member of A and any member of B when trying to figure out whether these clusters can be combined. And we're going to switch to average length instead and see if that improves the clustering that results. Okay, so that isn't a really huge difference in code. Let me see. Okay, right. What happens when we use average distances rather than furthest distances? Okay, so once again, we're producing our distance metrics exactly the same way, feeding in petal length and width. We are once again feeding those to the hclust thing, but this time we have an extra parameter that we're adding in here. We're specifying that the method will no longer be complete linkage, where we ask what the longest distance is between clusters, but rather the average length between clusters. Maybe this will give us a better separation. Now the plot has been produced as well. We can toss over to that. And we see that things look rather different, don't they? All we did was to change how it decided which cluster, how to evaluate whether clusters were close together or not. And now we see that the cluster that's popped out is completely different. Now again, I haven't specified which ones are red, blue, and green here, but we can apply just the same trick to ask how do we do on our scoring sheet. So let's take a quick look at that in a hurry. Okay, so once again we're applying the cluster cut function to to chop wherever it would give us 3 clusters in that. And we're looking again at the table for what cluster cut does versus the species that come out. Setosa, never a problem. They're always easily separable from the others. But now versicolor is set up 9-to-1 in cluster 2, and virginica is set up 98% to cluster 3. So all we did there was to change the method by which clusters were evaluated for distance from the complete cluster to the average cluster length, and suddenly our clustering gets a whole lot cleaner. So there are a lot of things that we can modify about this, even if you're just staying in Pythagorean theorem space. Okay, now we said a moment ago that the visualization stunk. So let's try to improve that. I'm going to use a complex bit of code, and we'll try. I'm sorry, my ggplot kung fu is pretty weak, but we'll try to walk through it just the same. Remember that ggplot allows us to layer different plotting functions on each other. So we start with this AES plot as a base. Remember, petal length versus petal width, determining color on the basis of species. On top of that, we've added points in different colors here. So here, we've specified that the points that we're plotting here have an alpha value of 0.4 and a size of 3.5. That may not make a whole lot of sense to you, but I'll provide this clue that alpha, in describing the imaging and plotting work that we do, usually refers to the transparency of the points. So we're creating a semi-transparent dot that's pretty large, 3.5. On top of that, we're layering on a point of standard size and transparency that is colored based on whatever cluster number that came out of here. Okay, I've also done a little trick here that this color for species is using the default palette, but the colors that I'm using for these scaled points is blue, purple, or yellow, because those 3 colors were not used in that plot. So let's look at what comes out of this. All right. Oh, one could really wish for a really, really good color of truth on these things, but we're not really going to get it, I'm afraid. All right, down here we have, I believe, black dots for Setosa that have been colored in blue, representing this cluster. What on earth is this thing doing? This looked entirely different on my screen. I'm sorry, but each of these dots then is compound. We have an internal dot that shows the species. We have a dot surrounding it in transparent colors that shows how it was classified by the cluster. And because it's ggplot2, we can layer these different things on top of each other to give us a whole lot better notion of how we're doing. So when we see things like green dots surrounded in blue, we see, or maybe that's in purple, I don't even know at this point, I'm sorry. We know that this represents an error because these are correctly matched. These are correctly matched. But then you have this thing like a red dot with a green surround, and you say to yourself, well, that didn't go so well. Okay? So you can show both axes at once, the truly known species against the classification that was assigned by the cluster. And it's random each time, so which pairing is best? I'll be happy to send you the code around for that. Okay. So, the next thing I want to talk about is really the last piece, and that is to evaluate the distance matrix that we use. So, to start with, I'm going to just do this in text if you don't mind. because I know that the visualization color is going to be a problem. Okay, so if we start by doing a Euclidean distance, you remember before we ran this distance function, but we didn't really feed it any parameters. Here we're just going to specify we want to use Euclidean distances to feed our clustering process. And we want to specify here that we're going to do average testing for figuring out which clusters should be brought together. So we see that when we cut to 3 clusters, we have a 50, 45, and 49 score rate. We have some amount of leakage of versicolor into virginica. We have a small amount of leakage from virginica into versicolor and vice versa. Okay. So all we're going to change now is to go to what's called a Canberra, let me pull this up, a Canberra distance instead. All right, I'm going to grab that text and throw it here. Boom. All right. Before we used Euclidean distances, this is Pythagorean theorem stuff. Here we used Canberra instead. Now Canberra is kind of an odd critter in some ways. In this data set, it causes some real problems to use this. But Canberra can make it possible to evaluate variables that are very differently scaled from each other. So where Pythagorean theorem tells us that the distance from distance along the hypotenuse is the square root of the sum of the squares of the A and B sides, Canberra asks us, what is the absolute difference between 2 values divided by the absolute sum of the 2 values? All right? So that can be particularly useful if you're comparing something like you care much more about the ratio of 2 values rather than their absolute sizes. So in this case, when we throw in Canberra as a distance metric, we see that suddenly Setosa, for the first time, is getting chopped into two sets, the 45 and the 5, whereas versicolor and virginica are being thrown together. The reason for this is that there are a small number of, there are 5 different members of Setosa that have substantially smaller petals than do the others. On a log scale, that's apparent. On the linear scale we've been plotting, it doesn't show up quite as well. So in this case, going to Canberra has forced this clustering software to chop apart Setosa, whereas calling versicolor and virginica identical. So you get different results depending on which metrics you apply for computing distances. We saw the Canberra versus Euclidean distance. You also get different clusters depending on which linkage rule you use for deciding which ones should be grouped together. We talked about the average distance, which helped us a lot with our clustering cleanness here. And we also talked about complete linkage, which asks what is the longest distance for any 2 members between A and B. Okay, so I hope that's been useful to you. I will send around the script that comes with this in the email that corresponds to this. But otherwise, the video will be posted online, and feel free to refer back to that the next time you have a clustering challenge. But I realize my background in ggplot2 is fairly weak, and every week as I do these tutorials, I think to myself, I am learning something new about this because it is clearly useful. All right, well, that's it for today's useful hour. Maybe we made it to 40 minutes. I think we'll call that a win. So have an excellent afternoon.